So today we're going to be modeling a continuously stirred tank reactor in two different scenarios. Our tank reactor in particular is going to be a tank with an inflow and then a mixer. That's not a great picture. We'll try that again. We'll have an inflow. I'm not an artist, in case you couldn't tell. There we go. And then we'll also have a mixer and some fluid level inside the tank. And then we're also going to have an outflow, and we're going to assume that the outflow has all the same properties as the material inside the tank, as the solution inside the tank. And then this whole tank is going to be inside a sleeve with water running through it, and we are going to assume that our reaction is exothermic. So the purpose of the sleeve is to move heat away from the reaction. And in this particular instance, before we go any further, this UA here is what we use to represent the rate at which energy in joules is moved away from the tank. So we'll just mark down UA, transfer of heat. And this isn't a universal constant or anything. It's particular to our situation. If we were to change the temperature of the water or the rate at which it flows past the tank, things like that, or maybe there's a gap in between the tank and the jacket, those things would all change the UA. But for our particular scenario, it's 5 times 10 to the 4th joules per minute Kelvin. And then from there, we know our inflow is 100 liters per minute. And since we're not explicitly given an outflow, we're going to assume that the inflow and the outflow are at the same rate in terms of liters. So we're going to have a continuous outflow, or a continuous state, or in a continuous volume inside the tank. So our volume is always going to be 100 liters. And our Q in equals Q out. Ran out of space up there. Let me try that again. Q in equals Q out equals 100 liters per minute. And then our volume is always going to be 100 liters. Our tank has a temperature, and it's important to note that this TC here, and I should also say these other T's, are the initial temperatures or the initial conditions for different parts of the system. For example, this TC is the initial temperature of the coolant solution. So TC, and then this concentration of A and this temperature 0 are the initial concentrations of temperature and the initial temperature inside the tank. And we know that because it's given in terms of a functional notation. I'm not sure if that's the correct term, but we know that that has to be at a condition of 0. And since we're modeling it in terms of time, we're going to assume that that condition is in terms of time. So we have CA and T0 over here. So that's our initial concentration of A inside the tank and our initial temperature inside the tank. And the reaction that is going to occur is A to B. And the way that we can determine the rate at which our material A turns into material B is through something called the Arrhenius equation. And basically that's going to say the proportion of the molecules of A inside the tank that are turning into B is going to be equal to some initial constant times E, and I believe it's negative E over RT. Let me just double check that actually. I'll pull it up. I don't know if you can see this, but I'm just pulling it up on my computer. negative e to the RT, and that e to the RT is simply the activation energy of the reaction divided by the universal gas constant times the temperature at whatever point in time we're at. And then this is the proportion this will give us the proportion of the molecules inside the tank that will turn into B, or molecules of A, I should say. And then to find the actual rate, or the reaction rate of A, we're simply going to have to multiply our K times our concentration of A. And this is per unit volume. So now our goals here are to find the changes in the concentration of A and the temperature. And we're also going to use some of these other parameters up here, but we don't need those quite yet. I should note that the temperature that is going to be coming in is going to be 350 Kelvin, and the temperature that's going to be flowing out is always going to be the same temperature as the fluid inside the tank. So here we're going to have the change in the concentration of A with respect to time is going to be equal to something. And in this case, it's helpful to look at this in terms of accumulation of A, because we have this term over here, and we can multiply that by V. So we'll just add this over here. So we know that we're going to have some amount of A turning into B at all times. And again, since this is per unit volume, we simply have to multiply by our volume. So I was going to try to do one of those fancy curly brackets, but that's not working great. Well, that'll do. And then we're also going to have, since again we're talking about accumulation, we'll just multiply the left side by our volume, and that'll give us the total amount of A in the system, or the change in A in the system, I should say. And then we're also going to have the amount that is coming in and leaving. So we're going to have Q times CA in minus Q times CA out. And since we know that our CA in and our CA out is going to be the same as the concentration of A inside the system, it's easier to write this as Q times the difference in the concentration of A that is coming in and leaving. And that is the same as the tank. And that's all we have to do to solve for the accumulation, and then to solve for the change in the concentration of A. All we have to do is divide this volume over, and we'll have Q over V, and then over here the volumes will cancel. So we are simply going to be left with this equation here, and that's our first equation. And then our second equation, we're going to have to go back to how temperature or not temperature, but how energy leaves the system through the change in sorry, I'm thinking of how to say this. How the energy leaves the system through the coolant jacket, how the coolant jacket works. So in this case, we have UA, and this is some rate at which the change happens. And when setting up UA, and there's a lot that goes behind this that we're not going to do, but in setting up UA, it makes it super simple. When we have the value UA, this is a constant that we multiply by some other thing, and the simplest thing that we can do is the difference in temperature between the tank and the coolant jacket. So we're going to know that our change in temperature, and it's going to be helpful to look at this in terms of energy initially. So I will come back to this. The left side is incomplete for now. Is going to be equal to our energy in, which we're going to have to come up with, minus our energy out. And then that energy out is going to be through flow and through coolant. So let me see if I can select this and move it down a little bit. There we go. So we'll still need a term for our energy in, so we'll leave that blank for now. But we do have our coolant term, and it is simply UA times the difference in temperatures between the jacket and the tank. And then our energy in is fairly simple as well. Or actually, you know what? Let me move back to the left-hand side of the equation here. We want to get this in terms of joules. And we have our heat capacity of the solution. We're going to assume that our heat capacity is the same for the whole solution. And that is going to be equal to 0.239, but we're not going to write that down for now. We're just going to leave it as our heat capacity, and that is in joules, grams, Kelvin. So we want to be left with only these joules, so we need to find something in terms of Kelvin, which we already have. So those will cancel, and then we just need something in terms of grams. But we don't have anything that's explicitly grams by itself. But what we do have is density and volume. And when you multiply density and volume, you are left with liters on this side, and then we'll also have grams per liter. And those liters will cancel. We're left with grams. Those will cancel, and then overall we are left with joules. On the right side, we don't have to do anything with the UA times T minus TC. That is totally fine how it is. From here, we just have to solve for the terms for our energy that's coming in, and then the energy that is flowing out of the system. Or not, I shouldn't say flowing out. A more accurate term would be the energy due to reaction. Because within this term here, we're actually going to be talking about both the amount that's coming in and the amount that's leaving. So we know that we have fluid of some temperature coming in, and we'll say that temperature for now is going to be Ti. And then, sorry, I'm not sure what I quite said there, blanked a bit. But we have a temperature of the fluid that's coming in, Ti, and then the temperature that's going to be leaving, which is going to be the same as the temperature inside the tank. Now again, we need to do the same thing we did over here, and we need to get this in terms of joules. So we have, we'll start out with Q, and we know that Q is in terms of liters per minute. And then looking at our parameters up here, we just need to find some things that we can use to multiply across, divide, and kind of figure out how to get this in terms of joules. So we have Q, and then you see we also have P, which will help us, or not P, but rho, our density, which will help us cancel out the grams. And then we also have our heat capacity, and we're going to assume the heat capacity is the same for this fluid that's coming in. So if we have our heat capacity, which is in terms of joules per gram Kelvin, well, we just need grams because we already have kelvins here, so those kelvins will cancel. And then we need to find a way to get grams, and we know we have our density still, and that is in terms of grams per liter. So these two liters will cancel, and we are left with simply joules. So again, we're taking a look at the difference in the temperature between what's coming in and what's coming out. This is just simplified. If we really wanted to, we can split it up into, it tends to actually help me think of this more if I think of it as Q times the amount that's coming in. So the total temperature of the stuff that's coming in, and then solving for joules, minus the total temperature of the stuff that's coming out, solving for joules. If we were to split this up, we could, but it's just easier to think of it in my head that way. It's sort of the same thing we did with the concentration above. And then to solve for the reaction, and I'm going to erase this just because it's taking up a lot of space and making it look kind of gross, but you know how we solved for joules on both sides. And then for the reaction, we're going to once again be using our Arrhenius equation. And we need to solve for that for the whole system. So again, we're going to have the term V times K times our concentration of A. And let me see if I can move this over to the side slightly more. There we go. And then for this video, I did decide to leave in a few more of my mistakes, just because I think it's important to kind of see some of the wrong thinking that might go into making those mistakes. And it looks like I erased my density over here. Probably better off erasing it than drawing it like that. Okay, so over here we have the amount of A that is turning into B in terms of the total system. But we need this in joules. And we need to convert the amount that's turning into B and use that to find out the amount of energy that is coming out of the reaction. And in this case, we happen to have the enthalpy of the reaction. And this is negative enthalpy of the reaction, so it's exothermic. And we can just write this down as negative delta HR. And in this case, it's 5 times 10 to the 4th joules per mole. So if we wanted to look at this, we can look at it in terms of joules per mole. This will give us liters, and then this will give us moles per liter. And then these cancel out, the moles cancel out, and we'll be left with moles. And then from here, all we have to do to, I'm trying to erase this, but this pen's being a bit difficult. All we have to do to write this in terms of the temperature instead of the total energy transfer is divide across by this V times our volume times density times our heat capacity. And that's just pretty simple algebra. We're going to divide by this whole term, and it looks like for the first term, for our energy flow through the system, it looks like the density will cancel and the heat capacity will cancel. So we'll be left with Q over V. And then over here, it looks like our V will cancel. So we'll be left with K over our density times heat capacity. And then for our third term, nothing will cancel. So we'll have volume times density times heat capacity. And we'll just rewrite this one more time instead of erasing through. We're going to have the change of temperature with respect to time. It's going to be equal to our flow rate divided by our volume times the change in temperature, or the difference in temperature between the substance coming in and the substance flowing out, plus our enthalpy of reaction times our rate of reaction, not in terms of unit volume, divided by our density times our heat capacity, and then all that plus, really I could just drag down this term instead of saving me, or instead of going through the trouble, but all in terms of our equation for the heat transfer out of the system divided by joules, really, because this will amount to answer in terms of joules, and this will be given in terms of joules. So we really just have to solve for temperature in that scenario. Sorry, I should say this will be in terms of joules, and then this will be in terms of joules, and then we'll be left with just a temperature change. But again, this is transfer of heat to the jacket. And then from here, all we have to do is throw these up into Python and then simulate the two scenarios that we have up here. One of them where we're increasing the coolant temperature and one of them where we're decreasing it.